It is my pleasure today to introduce our speaker, who is Aviv Rosenberg. Aviv is a PhD candidate at Tel-Aviv University, advised by Professor Yishay Mansour. Before, Aviv received a bachelor degree in mathematics and computer science from the same university. Aviv's main research interest is in the theoretical foundation of sequential decision-making. Aviv has done amazing work in theoretical reinforced learning, including stochastic and adversarial setting. In particular, Aviv has contributed to the theoretical foundation of exploration in Stochastic Shortest Path, a topic at the time particularly interested in. And today, Aviv is going to present the Minimax Regret result for SSP based on a reduction from SSP to finite horizon. Aviv, the floor is yours.
All right, thank you very much, Matteo. And thank you to all the organizers for giving us this seminar every week. So I'm going to share my screen. All right, you can see it, right? And yeah, so I'll talk about stochastic shortest path and the optimal regrets for this setting. And for this work, I worked with some amazing collaborators. So Alon Cohen from Google Research in Tel Aviv, Yonathan Efroni from Microsoft Research in New York, and Yishay Mansour from Tel-Aviv University and Google Research. All right, so I'm going to start with a little motivation, presenting the model, and then I'll get to our main results and discuss them a little bit. And then, as long as time permits us, I'm going to get into the details and describe our approach and the analysis, and maybe also the lower bound. So, in terms of motivation, I think the biggest motivation for stochastic shortest path is just that many of the applications that we want RL to work with are not really compatible with either finite horizon setting or discounted, just because in these applications, for example, in autonomous cars or robots or games, the interaction that we have with the environment is not for a fixed number of steps. And even more than that, the actions that we take actually affect the length of the interaction. And this is exactly what this SSP model tries to capture. And this is just an MDP where we have this special goal state, and it comes to model the fact that the interaction is going to end only when some condition is met. So really, the big advantage here is that this is a very general model, and basically any episodic task is going to fit here. And the finite horizon and discounted settings are actually just special cases of SSP. And the main difference between the SSP and the other settings is basically that we have this dual objective. So it's not like we're just minimizing our total cost, but we also need to reach the goal state in this interaction. And if we didn't reach it, then the interaction just never ends. And the challenges begin when these two objectives don't agree. So, for example, if I'm talking about cars, then I can just minimize my gas consumption, for example, by not moving, but then I'm not going to reach my destination. So I'm going to have to trade off these two things, and that's something that we'll consider throughout the algorithm and the analysis. And kind of the challenges that come with that is that the cost is not going to be bounded. So in terms of concentration and everything, that makes it really hard. And yeah, then like I said, the time is going to depend on the actions of the agent. So more formally, the model is just this MDP N that has an additional special state, G, called the goal state, that's not part of the state space, and the interaction goes on until we reach this state. So again, we have this dual objective. We want to reach the goal state, but we need to minimize our cost in this meantime. So full interaction is that we start in some initial state that doesn't have to be fixed, and while we're not reaching the goal, we're just going to take an action, suffer some cost, that has this expected value according to the cost function C, And then we're going to move on to the next state that's sampled from the transition function P. And the main concept that's really important in this SSP setting is the one of proper policies. So I'm going to call a policy proper if it's going to reach the goal with probability 1, no matter where I started. And so obviously we would like to play proper policies, because otherwise we can't guarantee that we're actually going to reach the goal state. And the basic assumption that we make here is just that there exists a proper policy. And this just means that that we can reach the goal state from any other state. So just like in other settings, what we're going to look at mainly is the value function, or the cost to go function, which is denoted here by J. So J of pi in state S is going to be the expected cost when I play policy pi and I start in the state S, again, until I'm reaching the goal state G. And since we also need to consider the time, or whether we're reaching the goal or not, we're also going to look at the expected time, which is T or pi in state S. And our benchmark is going to be the set of proper policies. So we are going to compare ourselves to pi star, which is the optimal proper policy. And just note that comparing to improper policies doesn't really make sense, just because there could be a policy that just goes in this zero cost cycle and doesn't do anything but has zero cost. So we want to compare to proper policies. And the two kind of important quantities that are going to appear in our regret bounds is kind of the scales of both these functions, the value function and the expected time. So B star is going to be the worst case over the state of the value function of the optimal policy, pi star. And T star is going to be the worst case expected time to reach the goal state when you're using this policy, the optimal policy, pi star. Okay, and the setting that we're looking at today is the setting of learning in SSPs, which means that the agent has no prior knowledge of either the cost function or the transition function. And we want to learn them from experience in the K episodes of interaction that we have. So each episode here is going to start in the initial state and end once we reach the goal state, if we reach the goal state. So again, we need to reach the goal state, and in this time we also need to minimize the regret. So here the regret compares the total cost that the agent suffers in these K episodes to the expected cost of the optimal policy. So K times the value of pi star from the initial state. And I think that an important thing here is that linear regret is not a bad thing in stochastic shortest path, or at least it's not a trivial thing. Just saying that your regret is not infinite is not that easy. You need to show that you reach the goal and that your cost is finite. So we need to keep in mind that it's a little different, but still we're going to get to the square root K regret. All right, so I think that's basically the model that we're going to study. We're going to minimize this regret. And if there aren't any questions, I'm going to go ahead and present our results. All right, so let's talk a little about what was done in this SSP setting. So it's not a new model, it's known for decades, but still somehow very understudied. So in the 90s, Betsekas and Tsitsikis and some more papers by them studied planning. So if you know the transitions and the costs, how are you going to compute the optimal policy? They show that it's basically under some conditions, it's going to be actually proper and you can compute it with value iteration. But then for learning SSPs, so it wasn't really studied at all until last ICML, where Matteo and John and all of their colleagues presented this online setting of SSP, and they showed the first regret bounds of K to the 2/3. And we also had a paper in the same ICML where we showed what's the lower bound here. It was this B star, so again, this expected cost of the optimal policy, times the square root of the number of states, actions, and episodes. And we also had almost matching upper bound up to a square root S term. And this square root S is what we're going to eliminate today. And also we're going to discuss this B star a little bit because it turns out it's not really the right scale here. And two other things that are related but not really directly, but worth mentioning is sample complexity in SSPs with generative models, which is a little different than regret. Interesting, but not very related, so I'm not going to get into that. And SSP with adversarial cost, which I studied, and also Liu Chen and Peng did great things there, and they talked about it in this seminar. And I just want to say that these are really kind of different settings, but a cool thing there is that there's actually a gap between the adversarial and stochastic case. Because in the adversarial case, your regret must scale with this T star. But actually, it's not really coming from the stochastic versus adversarial. It comes from the fact that in the adversarial setting, you see the costs only in the end of the episode and not throughout. But still interesting thing and a lot of things to do there. So now let's get to our results here. So basically what we do in this paper is really a black box reduction from SSP to the finite horizon setting. So it's quite a different approach than the previous papers where we kind of applied optimism directly into this SSP model. We go kind of around it and really solve finite horizon many times. And if we jump to the third point here, so if we take our reduction and apply it with the right finite horizon algorithm, which is this ULCBI that I'll talk about in a minute, then we actually get the optimal SSP regret. So here, the optimal one is square root of B star square plus B star. So this is a little different than the previous slide, where in the previous slide, we only had this B star square. And when B star is smaller than 1, so the dominating term here is going to be this B star and not the B star square. And we actually show that this is tight. So we also have a lower bound that shows that this is actually the right scale. And it's not like the previous results were wrong. It's just that there the cost function was deterministic. And we're used to it not really making a difference in RL. But it turns out that if the cost function is stochastic and it has a B star smaller than 1, then actually the correct regret is square root of B star and not B star square. And this is what our lower bound shows.
So Aviv, I have a question here. So if I remember correctly, the previous bounds made the assumption that the coasts are lower bounded by some minimal coast, and then this minimal coast was showing up in the bounds as well as like 1 over C min. But you were not showing that on the previous slide. And do you still have these factors in this work, or is this related to this B star and B star squared?
So so in the previous works, the approach was first to solve this with this C-min assumption and then eliminate it. But here we're not taking this approach, and this is why the C-min does not appear. But also in these works, these regret bounds are after the C-min, so C-min does not appear. Okay, good. So finally, to get to this regret bound, we needed a finite horizon algorithm with a regret that does not scale with h, that only scales with the expected cost of the optimal policy. So this ULCVI algorithm, which is not really new, it's just an optimistic algorithm, but the analysis here is quite different. So for it, we showed that in finite horizon, so I'm going to use these hats when I'm talking about finite horizon. So in the finite horizon setting, we can actually get this regret bound that depends only on the expected cost of the optimal policy and not really scales with h. So h is going to appear here in the logarithmic factor, and obviously it has to appear in the additive term. Oh, this is also, I think it's also an important result. It shows us we don't really need h in our finite horizon bounds.
So Aviv, there's a question in the chat. So what is m here?
Yeah, sorry. So in the finite horizon, I'm going to use m for episodes and hat for all the value functions and regret. And in the SSP, I'm going to use k for the number of episodes.
Right. So it's number of episodes and not number of total time steps.
No. It's the number of episodes.
And okay, so what was the hat?
So here the hat is the regret in a finite horizon model with m episodes.
Okay, and you just like hats, and okay.
The hat is going to separate finite horizon from SSP. Okay. So a final note here is about this additive term. And the little annoying thing here is the inverse dependence in this B star, which when B star is really, really small and we don't have that many episodes, then this is going to be kind of dominating. And I mean, we didn't really focus on that, so we focused on the main term here and making sure that this is optimal. But it looks like just an artifact of our analysis and not something so we did leave it for future work to just eliminate this annoying dependence.
So would you say it's an artifact of the analysis or the algorithm design rather?
No, the analysis. I think it's the analysis.
Okay.
I'll point out where in the analysis it's coming from. Okay. So few notes about what do we actually need to know in order to apply this reduction. So the way that I'm showing it here, we need to know both T star and B star. But actually this B star, we can estimate it on the fly. So let's focus on the T star. And I think it is a really interesting problem whether we do need to know it in order to apply a reduction to finite horizon. So on the one hand, it kind of looks inherent because you need to set your horizon somehow. But on the other hand, it could be solved by some kind of doubling trick. So I don't know the answer here. But anyways, it has its nice properties that it is a parameter of the algorithm, this T star, because we can using it, we can really control the complexity of the algorithm. So if we set it to be some x, then we can say that the total computational complexity of the algorithm over all of these k episodes is going to be of order x, or x log k, so logarithmic in the number of episodes, which is nice. And the total number of time steps is also going to be controlled by x, so it's going to be x times k, so roughly x per episode. And in this case, our regret bounds are going to hold against all the policies that their expected time is bounded by x. So in terms of compute or number, you want to compete against the best policies that you can compete against. So I think this is useful. And this is a good point to point out to the new actually can achieve similar regret bounds without knowing T star in advance. So that's a really important result. But again, I think in terms of computational complexity, our algorithm has its advantages in the sense that you just need to, kind of run finite horizon, which is something that people are used to. All right. So two final notes. One is about the finite horizon results. So there is this recent paper by Zhang et al. That also showed that the regret in finite horizon does not need to scale with h, only logarithmically. But there they have a much stronger assumption. So there they have the assumption that in every trajectory, the cost is bounded by 1. But here we don't really have any assumption. It's just denoting the optimal expected cost by B star. So I think it's a nice generalization of their result and really shows what is kind of the correct rate for finite horizon. And finally, the reduction to finite horizon was used in adversarial SSPs before our paper. And there, it's quite different usage, because there in each SSP episode, they run one finite horizon episode, and then if it doesn't reach the goal, then they just try to reach the goal. While we are just going to run the finite horizon over and over again. And this is what's going to give us the optimal regret, and the regret that does not scale with this T star. But again, I don't think it's really comparable, because the settings are quite different. All right, so these are the results, and now I'm going to get a little more technical and present the reduction and the analysis. So the reduction is going to be very simple. You just take your favorite finite horizon algorithm, and you set the horizon h to be of order T star, so T star log k. And the idea here is just that you want the finite horizon cost of the optimal policy to be close to its SSP cost. And this is why you need h to be of order T star. And then, as long as the interaction continues, so for all the k episodes until you reach g in each episode, you're just running one episode of A, so one h steps episode. And if you do reach the goal state in this h steps, then you just feed the trajectory as is to the algorithm A. You just make it of length h by putting like g in the end of the trajectory. But if you didn't reach the goal state, then you want to somehow signal to the algorithm that it needs to get to the goal state, because in the finite horizon model it may not be something that you want to do. And therefore, you penalize him for not reaching the goal state by giving it a terminal cost of 8 times this B star. And then you just feed the actual trajectory together with this terminal cost to the algorithm, to A. So that's it. That's a reduction, very simple, and almost no overhead over the finite horizon algorithm. So just really, you just inherit the computational complexity of A, and yeah, that's it. So now, the interesting thing is going to be in the analysis. If everyone's okay up to here.
Sorry, Aviv, I have a question about the planning. When does it happen? Because it's not explicitly written in the algorithm.
Yeah, so the planning is happening within the algorithm A, right? So some algorithms are going to plan at every episode, and like the algorithm that we give plans only logarithmically a number of times. But yeah, it's totally up to the A algorithm.
Okay, thanks for clarifying it.
All right. So for the regret analysis, we're going to have to be a little more technical. So let me introduce some more notations and some more hats. So we have the SSP model, M, and in parallel, we're going to have our finite horizon model, which is M hat. And they are almost the same, so they have the same transition function and cost function. But this M hat, apart from being finite horizon, another unique thing is that it has this set of terminal cost. So in each state S that is not the goal state, you're going to get a cost of A times B star in the end of the episode. And I'm going to call each episode of the finite horizon algorithm interval. So I'm going to have M intervals for the finite horizon and K episodes for the SSP, right? And this M, the number of intervals, so this is a random variable. This is something I need to bound in order to get my regret bound, and also in order to know what's the compute cost of my algorithm, right? Because I'm running finite horizon and I'm saying it's cheap, but it's a question of how many times I'm going to run it. And this M is going to be of order K, basically. So now, in each interval, what's happening is that the algorithm A, the finite horizon algorithm, is choosing its policy, pi m. And notice that it's not stationary. It depends on the horizon. And then we're observing the trajectory, um, and we feed the algorithm the cost, C1m through CHM, along with the terminal cost, which is hat CF at the final state of the interval. So if this final state is the goal state, then it's 0, and otherwise it's A times B star. Again, just a notation for the value function in the finite horizon model. So it's going to be just with a J with a hat. And the SSP cost was J without the hat. And so before we start actually bounding the regret, we're going to have some properties for this finite horizon algorithm. We can't just take any algorithm and expect to get optimal regret bounds. But a good note here is that you can actually run this reduction basically with any algorithm, and as long as you have some regret guarantees in the finite horizon for that algorithm, you are going to have a regret guarantee in the SSP model. The difference is that if you're not using what I'll introduce as admissible algorithms, then your regret will scale with T star and not with B star. But for now, let's assume that we do have some good properties for this A algorithm. So I'm going to call this A algorithm admissible, and this basically just means that it's model-based and it's optimistic. So model-based meaning that it keeps these estimates of the cost function and of the transition function. And optimistic means that it's going to be greedy with respect to the estimated Q function that it computes, and that this Q function is going to be bounded by the actual optimal value in this finite horizon model. And all of these things are holding, obviously, under some good event that is making things a little harder technically, but I'm totally ignoring them in these slides. So just keep in mind that we have this one. And finally, so this is not really an assumption on the algorithm, but it's just kind of a property that all optimistic algorithms are going to have. And this is how many samples do we need from some state SA so that we can say that the error in our estimation of the transition function and the cost function is of order B star over H. And the idea here is that we want to say that if we sample all the state action pairs enough, so at least like omega times, then the optimistic policy that we choose is going to be with actual value, not with estimated value, of B star. And this is what's going to let us have that. So
wait a second, Aviv, I have some questions. So you said that, well, these are like fairly general conditions, but maybe I would argue that, well, this is a bunch of conditions in the end. That you need optimism. I guess optimism means that you have this property for every state, right? Not just for the initial state.
Yeah.
And also you need your Q function estimates to be deterministic, I imagine. So it cannot be a randomized algorithm, but you need to be greedy with respect to a deterministic Q function that is optimistic.
Right. So, I mean, to get this optimal bound, basically what you need is a model-based optimistic algorithm, which is limiting. But if you don't care about, optimality, then basically any algorithm is going to work. I'm not going to need any of these conditions to show a regret that scales with T star instead of B star.
Okay, so these are the conditions for the regret to be optimal, or for the algorithm to make sense at all?
These are the conditions for the regret to be optimal up to the regret bound of the A algorithm. Right?
And do we have a regret bound for algorithms that do not satisfy this?
So we didn't do it in the paper, but actually it's really simple. I mean, if you just take the terminal cost to be of order T star and not B star, then you don't really need an analysis. It's just everything is going to work and you're going to get the regret bound that scales with T star.
Okay.
The complicated thing here is to keep this dependence in B star and not T star. And this is why you need these conditions.
All right. Okay. Gotcha. Very good.
All right. Okay. So yeah, with these conditions, we are going to prove optimal regret bounds. So from now on, we assume that our algorithm is optimistic model based, and that we have. I mean, the algorithm doesn't know it but for the analysis purposes, we have this omega that tells us that we have pretty good estimates in this state action pair. Okay. So now we're actually going to start with bounding the regret, and we will start by relating the regret of the SSP and the regret of the finite horizon. So here I'm just starting by writing the regret, the sum of costs as sum over intervals instead of sum over episodes. And then from here, I'm going to want to translate it to finite horizon terminology. So this J of pi star, this is the SSP value, and I want to translate it to the finite horizon value, J hat. And this is just going to hold because I set my horizon to be long enough, so they're going to be close. But the main problem here is that I have this mismatch between the number of intervals here and the number of episodes. So here I'm summing over m intervals, but I'm comparing to k times the value of pi star. And the way I'm going to duplicate this value from k times to m times is using my terminal cost. So the idea here is that every time we didn't reach the goal state, then I know that I've received a terminal cost. And this terminal cost is what allows me to kind of roll the regret to the next interval. And then I can get kind of a good translation to finite horizon, where in each interval, I'm comparing my cost to the value of the optimal policy. So now from here, I can just split this to the regret of my finite horizon algorithm of A, and to this deviation of my realization of the costs from their expected value, from J hat. And this deviation term, so it's this martingale term, and but bounding it just like that is not enough because every term here is of scale h. So I'm going to get like h square root m, which is bad because I want it to be B star and not T star. So this is...
Yeah.
Yeah, sure.
A quick question about the very first thing was the regret definition and like the way you use the regret here. It's like you're kind of cutting short the episodes when the goal state is not reached, right? Like you can just like reset to the beginning. And if an agent decided to do that like after 1 step or like 0 steps or whatnot, like then it wouldn't incur any cost, or like it would incur very little cost. So like the original regret definition, you were even emphasizing that some of these episodes could be of infinite lengths or whatnot, which is avoided here because you're just resetting, but then stops. Okay, so I'm misunderstanding something here.
Yeah, it's not avoided, it's just, it's hidden in this M, because this number of episode is a random variable. I mean, every H steps, if we're not reaching the goal, then we're just going to a new interval. And then this M is going to be large.
From the state that you landed in the last interval, right?
Yeah, it will be from the last state that you landed.
There. So it's just continuing, it's just like chopping up the long thing into multiple intervals. All right, okay, good. Yeah, that I think, yeah, sorry for missing that. That explains a lot.
Okay, good. All right. Okay, so now, so we have this deviation term that we need to bound more carefully. And finally, we have to bound this M, because this is what going to actually control the regret, the number of intervals that we have. So now I'm going to get to kind of the main argument.
Sorry, Viva, I have a question about the previous slide. The relationship between the SSP J definition and the finite horizon definition, because you write that they are approximately equally in the bottom of the slide. There is a bias there. How do you control the bias? Is of order 1 over k?
Yeah, it's of order 1 over k. It's just controlled by the length of the horizon. So if I'm taking the horizon to be t star log k, it's going to be of order 1 over k.
Okay. So pretty much this means that you can reduce any SSP problem that normally is difficult to solve into a finite horizon and get any epsilon accurate solution.
Yeah.
As long as you need to know T star, right?
Yeah, you need to know T star. That's the problem here.
Okay, thanks.
All right. So now I'm going to get to the main arguments of our analysis. And the main argument is this separation between known and unknown state action pairs. So the thing, and a nice thing here is that this is also going to be the main argument for the finite horizon analysis. So we're kind of getting them 2 for 1. So the main thing that we want is that in an interval, our cost is going to be of order B star and not H. So there's this gap between B star and H, and we want to be closer to the B star. And obviously in the first episodes, in the first intervals, it's not going to happen because we don't know anything. But once we have some reasonable estimates, it should be okay. And this is the way we use it, is through this definition of known state action pairs. So once I have at least omega visits from S and A, I'm going to call it known. And then I'm going, for each interval, I'm going to look at my total cost until I've reached one of these unknown state action pairs or the goal state. Okay, so I'm not looking at all the cost, only on the cost until I've reached an unknown state action pair or the goal state. And this is denoted by Cm, where Hm here in the sum is this point where I reach this unknown state action pair or the goal. And if I didn't reach them, then it's just going to be H, the last step of the episode. And the key lemma here is that for this Cm, for this cost, its expected value is going to be of order B star and not H. And even more importantly, the second moment is going to be of order b star square plus b star. And if the cost function was deterministic, then actually it was just b star square. And the way that we prove this is by looking at an MTP where all the state action pairs are known. So we're taking all the unknown state action pairs and contracting them with the goal state. And then we have an MTP that has the goal state and known state action pairs. So there we have a good estimation or a reasonable estimation all around. And therefore, we can say that our optimistic estimate is close to the actual value of our policy. And then we can say that it's of order B star. And then kind of to amplify it and get the second moment bound, we need to, we use that it's actually of order B star for all the states. So the value function is uniformly bounded by B star in this MTP. And with this argument, both the number of intervals is going to be bounded and the deviation term is something that will bound. So for the deviation term, we're just going to take each interval, split it to the times before HM and after HM. So before we reached the unknown state action pair or the goal and after it. And since after every omega visits to each state action pair, it becomes known, we can bound the second sum, the sum over cost after we reached an unknown state action pair by some constant, by h times omega SA. And for the first term, so we have this martingale, but now we know that the second moment here is of order B star square plus B star. And therefore, with this Friedman argument, we can bound it by square root of B star square plus B star times the number of intervals. Right? And finally, we need to bound the number of intervals. So for the number of intervals, we are actually going to use the bound on the first moment, not the second moment. And the nice observation here is that in each interval, we actually have a constant probability of at least 1/2 to reach the goal state or an unknown state action pair. And this follows simply because of Markov inequality. So we know by this key lemma that I showed you that the expected cost until we reach an unknown state action pair or the goal state is bounded by 4B star. So there it was an order of B star, but here it's 4B star. But also we know that in the last step, we have this terminal cost of 8B star if we don't reach the goal. So just by Markov inequality, this means that we are not going to reach this 8B star terminal cost with probability of at least 1/2. And then once we have this observation, we again use kind of this Friedman inequality argument where we denote by xn the indicator of whether or not we have reached an unknown state action pair or the goal state in interval n. And we use the fact that the sum of conditional expectations is going to be basically of the same order as the sum of realized indicators. And the sum of realized indicators is bounded by k plus omega SA, because after every visit to SA, after omega visits to SA, it's going to be known. But on the other hand, the sum of conditional expectations is at least the number of intervals over 2 because of this observation. So finally, the number of intervals is going to be of order k plus this omega SA. And this kind of sums up the analysis. So this leads to the main reduction theorem where we decompose the regret, bound the deviation, bound the number of intervals, and then we can bound the regret in the SSP model by the regret of the finite horizon algorithm A in this k plus omega SA intervals, plus this lower order term that comes from the deviation term. And here notice that there are no random variables. So before that we had m, but here it's just in terms of k and s a b star. So now to here, we can just plug in the regret of ULCVI or Euler or any other like optimistic regret minimization algorithm. And here we get this optimal regret bound. And where this inverse dependence comes from is from the omega bound for this ULCVI algorithm. So for that, we show that we need like something that depends on 1 over b star squared. But this is really a very rough bound. It's not tight at all. So this is where we believe that that you can avoid this inverse dependence. All right. So this sums up the analysis, and yeah, and I think that that I'm going to skip over the lower bound, right? Because I have a few minutes. I can maybe I'll just give a few words about it. So actually, it's really simple and nice. It's just that think of a multi-arm bandit where you have 2 arms, one with expected value of b star, the other with b star plus epsilon. So in order to distinguish between them, you're going to need b star over epsilon squared samples, which means that you'll have square root of b star regret. And then you can obviously add more arms, and you can just embed many of these multi-arm bandit problems in an SSP. So you just take one in each state, you initialize the state in each episode randomly, and in each of them you just go to the goal state in one step. And this gives you a lower bound, which is really simple and nice. And I have also the previous lower bound, but I'm going to skip all that. So just let me conclude. So what I showed you here is really just a simple and fast reduction from SSP to finite horizon. And I showed you that the optimal regret for SSP is square root of b star squared plus b star times SAK. And another important thing is that this is actually kind of the right regret bound also for finite horizon algorithms. So they don't really need to scale with polynomial lists with the horizon. In terms of open problems, so the interesting open problem is whether we actually need to know this T star in order to perform a reduction. And kind of the smaller issue is how to avoid this 1 over b star dependence in the additive term. And I think kind of the more philosophical question maybe is what's next with this SSP model? Because it looks like with this paper and this new paper by Tauberish that the tabular case is pretty much closed. I guess it's an interesting question if we're going to go to functional approximation here, or is it worth it, I guess. And I see that Gregor has opinions on that. So this is where I'm going to finish. So thank you very much, and hope you enjoy this.
Yeah, thank you.
Thank you.
So I have a question. First of all, thanks for the talk. It was very nice. It was very clean. At a certain point, you mentioned that you can estimate a B star on the fly in one of the initial slide. Can you comment a little bit on that, because then you didn't mention how to do that?
Yeah. So it's something that we also did in the adversarial case, and Peng and Liu also did it. Basically, you can just use the first visits to every state in order to estimate the value in that state by using like an algorithm, a regret minimization algorithm that doesn't need to know B star, for example, our previous algorithm. You just need to run it for some fixed number of episodes, and then you get another term another additive term in your regret, but it's not really high. It's not really a high term, and it doesn't really bother the reduction. It's just that every time you reach a state that you haven't visited enough, you stop the reduction and you run an episode to estimate its value, and then you have this doubling over the value.
All right. So I have some more technical questions, which is also it seems to me again that maybe those conditions that you've listed, maybe I'm just not understanding the role of all of those, or maybe I was missing something, because it seems to me that in these episodic MDPs that you have to face, basically one challenge is that the initial state is always going to be different, right? And it's not going to be stationary, right? So it's not really a standard reduction to the episodic case in that sense, because there you assume that, well, it's always a fixed starting state, or it's IID or something.
Yeah, right. I didn't really write those conditions formally, but you're right. There is a condition that the regret mode needs to hold against an adversarially chosen initial state.
Yeah, I mean, to me, that assumption about this uniform optimism over all states, it kind of seems to imply this, or no?
No, basically every optimistic algorithm in finite horizon, at least, you're going to have optimism over all states together.
Yeah. In the tabular case, there's also this.
Yeah.
In the linear case, there's this Eleanor algorithm by Andrea Zanet and Matteo and Alessandro. I think Matteo, maybe not you, but right. Yeah, but they don't have optimism in all the states. Mm-hmm. They only have optimism in the initial state.
Yeah, but they solve like a global.
Yeah, right. It's a complicated global optimization problem.
Right. Yeah. So it's a little different. Yeah. I mean, it's. That's why we made these assumptions that that it's optimistic and that it's greedy but yeah.
All right. Yeah.
So maybe in this direction, you mentioned that it's basically any model-based algorithm. Where is the model-free algorithm breaking is this optimism, right? Because you need to have it at each time step at every state of the NDP, right?
Yeah. So the problem with it's not really a problem. It's the way that the analysis works right now is that we are kind of comparing the estimated model and the true model, and then we want to say that if you have enough samples that they're close in some sense, and then your optimistic value and actual value are close. If you have a model-free algorithm, you're just going to have a different argument on when is your optimistic estimated value close to the true one, and then you can do it.
Right. It makes sense. Because indeed, that's, I think, is one of the possible directions for SSP, since designing model-free algorithm, because pretty much all the entire model-based right now.
Yeah, I agree. That's probably the most interesting direction right now.
And then regarding your last comment about whether or not this can be extended to function approximation, I think that there is a paper on arXiv that does linear function approximation.
Yeah, there is a new one. I haven't gotten to reading it yet, but there is.
We neither, or at least I didn't get there. So let's not speculate about whether they are model-based or model-free. I guess model-based and linear is a bit shaky.
Yeah.
So Concon had a question. I don't know whether that was addressed. Concon, do you want to ask your question? Well, it's similar to the previous questions, whether you can just use UCBVI. for the purpose of reduction, why do you need use ULCBI in your algorithm?
You can use it. Basically, the only thing that you need is that you need to bound this omega, and that you want a regret that scales with this B star and not with H. So the main problem is that all the current bounds are with H, which is T star here.
Yeah, I see. Okay. So some unrelated questions about B stars. At the beginning, you said that you can learn B star easily. That's super easy. So how does that work? I've been thinking about it a little bit, but it doesn't seem that easy to me.
Yeah, so I just answered Matteo about it actually, but you just, yeah, that's okay, I'll tell it again. So you just, you start your reduction, and every time you reach a state that was not visited some number of times, then you're going to stop the reduction and run another regret minimization algorithm that does not need to know B star, for example, our previous algorithm.
Mm-hmm.
And then once you have enough visits from that state, you're going to use its average cost in order to estimate the value of the optimal policy from that state. And then you can use it to kind of perform a doubling trick over B star.
Not sure I fully understand. So you're running your algorithm, and then whenever you encounter a state which has not been visited sufficiently many times, like you have a guess of B star, I guess, and whenever you encounter a state that is not visited sufficiently often times, then you switch to an algorithm that doesn't need to know B star. You run it until...
You run it until the goal state is reached.
Okay,
right?
So you want to get to the goal.
And once you have some number of visits from that state, then you say, okay, now I can estimate.
Once the goal is reached, you switch back to the algorithm. And then again, if you have, so it's basically you have this mixed algorithm.
Yeah.
You keep running this mixed algorithm, and then what happens once you have?
So once I have enough samples, then I can use the average cost that I had from that state, from every time I started in that state, in order to estimate the value from that state.
You have to do this for every state?
Yeah.
And then once you have all these estimates from every state, like
so I'm not guaranteed to have it from every state, but if I don't have it for some state, then I don't visit it a lot.
Okay, all right. I need to think about this. And so in the lower bound, you said that for a banded B star, like the regret scales with B star, that's definitely not true for, let's say, Gaussians with a mean of B star.
You mean here? Just if you have two arms, then just by the Chernoff inequality, when this B star becomes small, then you are going to need...
Only when B star goes to 0? Okay.
Yeah, I mean, if B star is close to 1, then it's not really interesting. Yeah. But
this would say that if B star is 0, then the regret is 0, which is, again, I don't think that that's true.
If B star is 0, then you are going to have constant just regret, because you're going to try each arm until it gives you a cost of more than 0, and then you're going to stop trying it. So each arm, you're going to suffer cost from it only once.
So wait, in this problem you have Bernoulli rewards or Gaussians or?
Yeah, Bernoulli rewards.
Oh yeah.
Okay.
So Bernoulli is the important part here.
Right.
Yeah. Sorry, it's Bernoulli, right?
Yeah. Okay. All right. And why Bernoulli is okay? Because it's a lower one, so you can just like, yeah. Got it. For sure. Okay. Okay, thanks. So regarding function approximation, speculation, whatnot, I haven't seen the paper yet either. So you have this generic reduction, so one would think that, oh, yeah, like you can try it. And with sufficiently many assumptions, it should work. So what's the main challenge? I guess like one of the main challenges is that the underlying algorithm, to get optimal regret, the underlying algorithm should have this horizon-free bound that you're reducing to, and like how many times have we seen this for the functional approximation setting, like which algorithms to use, what setting to use. I see. Okay.
Yeah, I guess in general for finite horizon to be horizon free for linear MDPs, for example, is quite interesting.
Mm-hmm. But I suppose the assumption, or like the part in your analysis that immediately breaks, is this distinction of known and unknown states.
Yeah, definitely.
But that can be addressed probably just by looking at the features.
Yeah, you can look at the directions of the features. I guess something like that should work.
So the linear MDP setting, which is not the mixed parametric model or whatnot, the mixture model, but the more non-parametric style, for which you only have model of 3 algorithms, right? Gene, whatnot. So that's model 3.
Right.
So now we're talking, I guess, about something interesting, right? Because if somehow it was crucial that you have a model-based approach in the finite case, then like how will it work? Let's say under that setting.
Yeah, so I think the model-based is because you need somehow, when you have this reduction, you need to somehow formalize the guarantees that you have from the algorithm. But if you're going to not work black box, then I don't think that you really have to be model-based.
All right. Okay. So maybe this pushes one to do a non-black box-based analysis.
Yeah.
Yeah, I don't know. Okay. I'm not sure.
And anyway, if you want, you can think of this LSVI UCB algorithms as model-based as well. Like we had this paper with Kira last year at NURBS where, well, maybe that construction is like a little bit forced, but in the end, it is a model-based construction.
Everything is model-based. Yeah.